The final part of our lesson in 6.1 covers finding the area of triangles and some other application problems involving bearings. In this chapter, we're actually going to look at a number of different ways to find the area of a triangle. I think almost everyone is familiar with the classic area is equal to 1/2 base times height. We remember that from our middle school days. We probably are familiar with a number of other ones, but a couple of other ones that I want to mention in this course. So first off, we have also the area of an oblique triangle being 1/2 times the product of the two sides and the sine of the included angle. So just want to make sure I highlight here that this is actually what we call an SAS case, which we'll look more at in the next section. But in an SAS case, you can actually find the area of that triangle by essentially multiplying all the given information. So the two sides, the sine of the included angle, and dividing all that by 2. So here's a really quick and basic example of this. So if you were given the triangle, and again, I'm just going to draw this arbitrary triangle here, not saying that this is actually how it looks, but this angle here being 5 degrees in 15 minutes. And if you remember early on when we discussed angle measurement, 5 degrees, 15 minutes, you can actually use your calculator and change this from your classic mode to what we say DMS or degrees, minutes, seconds mode. But hopefully most people can see here that 15 seconds is 1/4 of, excuse me, 15 minutes is 1/4 of a degree. So this is the same thing as 5.25 degrees. 15 minutes is 1/4 of a degree. So angle A here would be 5.25 degrees. What else are we given? We can say that this side here is side B, so B is equal to 4.5. Side C here is equal to 22 centimeters. And we don't know angle A or, excuse me, we don't know angle B or C. So we're given, in this case, two sides and its included angle. Therefore, this makes it an SAS case, which means that we can find the area of this triangle by doing 1/2 the two sides that are given to us, so 4.5, 22, times the sine of the given included angle. So the sine of 5.25 degrees. So at this point, you could just punch all that into your calculator and say that the area of this triangle is approximately 4.53, and the units that were given were centimeter, and since we're finding area, we would say centimeters squared. So there's the area of this triangle, okay? Go ahead and pause the video and try number 2 on your own, and you can find the solutions for this in our Google Classroom. The next thing I want to discuss is bearings. Now, I know that this might seem like deja vu for some of you because we definitely discussed bearings already in this class. Another type of bearings that I want to go over is bearings when we are dealing with air navigation. Anything where we're navigating in the air or in the sky, we use a slightly different type of bearings. We're used to bearings being angles that open up from the vertical. So if this is north, east, south, west, we would say a bearing something like this, if this angle were 30 degrees, we would say north 30 degrees due east. This is typically how we've written bearings in this class. And if we have an angle that goes beyond 90 degrees, so for example, let me just go ahead and erase some of this here. If we go beyond 90 degrees and said something like, let's say this angle were 10 degrees, if this angle were 10 degrees beyond the 90-degree horizontal, you would actually look at this bearing here and say it's south 80 degrees due east. That's how we've done it so far. Well, when we're dealing with air navigation, we actually are allowed to extend beyond the 90 degrees, and we would write this as what we would say a 100-degree bearing. We would say this is a 100-degree bearing because you have the 90 degrees plus the additional 10, and would just say a 100-degree bearing. So when we're dealing with air navigation, you are allowed to extend beyond 90 degrees and go all the way to 360. So let me try a different color. If I said something like this angle here were, let's say for example, this angle here were 20 degrees, In air navigation, we would say that this entire bearing here, this entire bearing is 340 degrees, okay? So when we're dealing with air navigation, bearings are measured in degrees clockwise, starting from the north vertical line all the way around. So you can go all the way up to 360 degrees. So that allows us to work with a couple of different types of problems. I want to do one with you all right now, and then give you some time to work on some of these other ones on your own. And you can check your solutions again in Google Classroom. But let's try one together. So we've got a problem here where a plane flies 200 kilometers with a bearing of 50 degrees from Gotham City to Metropolis. So I'm going to go ahead and just label Gotham City as this point here. And it is flying with a bearing of a bearing of 50 degrees, but it flies a distance of 200 kilometers. So think about what that bearing of 50 degrees looks like. Well, I'm going to draw my north vertical, or my vertical line, of 50 degrees from Gotham City to Metropolis. That means I'm going to be opening up 50 degrees this way. So this angle here is 50 degrees. And that would mean that Metropolis is somewhere up here. So Metropolis is here, there's my bearing, and the only thing I'm missing now is my distance of 200 kilometers. So that's the distance there. So the plane goes from Gotham City to Metropolis. Now let's read the next part. The plane then flies 350 kilometers from Metropolis to Washington, D.C., which is due east of Gotham City, which is another way of saying it's directly east of Gotham City. So Washington, D.C. is somewhere around here. I'm going to label this as DC. So the plane flew this distance of 350 kilometers from Metropolis to Gotham City. What we are asked to find is the bearing of the flight from Metropolis to Washington, D.C. Now, before we set off doing that, let's make sure we understand what exactly that bearing would look like. So from Metropolis to D.C., if we were dealing with normal bearings, or the bearings that we're used to working with so far, we would be talking about this angle up here. However, since this is air navigation, the bearing that we're actually discussing is all the way from this vertical line all the way down to that line there. Now, this is clearly an angle that's greater than 90 degrees. So one way of kind of visualizing this is finding a way to determine this angle here. Let me zoom in on that picture a little bit. This angle here, the angle from that horizontal to the path that we traveled, or this plane traveled from Metropolis to Washington, D.C. We're going to leverage the fact that this is a right triangle here. That's going to help us out. So to determine the missing angles, we're going to use some basic geometric properties here. And we're going to start back with this given information. Why do you think that I gave you the bearing from Gotham City to Metropolis? That has to play a role here, and it absolutely does. We can say a couple things. We can say, all right, well, if that angle is 50 degrees, we know that the complement of this angle here, this angle here has to be 40 degrees. So you can use that, and you can also use the fact that this is indeed a right triangle here, meaning this angle here is 50 degrees using alternate interior angles. And we can then start setting up a couple of different things here. We can say the following. We could say that this angle here is 40 degrees. So we can say that in this larger, and let me just kind of see if I can highlight this for you all. In this larger oblique triangle that we're dealing with here, we can use the law of sines because we know that the angle 40 degrees, so this angle here, we know that this angle 40 degrees, its opposite side is 350. So I can go ahead and write that to start. I can say, all right, the sine of 40 degrees over its opposite side of 350 kilometers, right? The sine of 40 degrees, and its opposite side there, 350. We can at least establish that. Now, what else do we know? We know that if I want to find out this angle up here, again, I can use alternate interior angles to know that, hey, this angle that's within this larger oblique triangle is going to be congruent to this angle up here because they are alternate interior angles. These are two parallel lines that are cut by a transversal. So if I can figure out this angle down here, then I know that its alternate interior angle will be congruent. Once I have that angle up there, then I can just add it to 90 to figure out my bearing. So what do I know? I know that the sine, and I'll just do this in the same color, that the sine, and I'll just call this DC, the sine of angle DC, so we can see that reference point, and its opposite side divided by its opposite side, which is 200, that ratio is going to be proportional to what we initially set up. So from here, just using some basic calculation, we can say the sine, angle DC is going to be approximately equal to 21.55 degrees. So this angle here is approximately 21.55 degrees. If that's 21.55, that means this angle down up here is approximately 21.55. And then from here, we can then say, all right, my bearing is going to be 90 degrees plus approximately 21.55 degrees, which is approximately 111.55 degrees. And let's write our answer as a sentence. So the bearing, so that way we are clear about what we exactly are stating. The bearing from Metropolis to DC, or Washington, DC, I'll just write to DC, is approximately 111.55 degrees. There's our bearing there. And you should box that, but I'm not going to do that right now. Now, take a step back before I go finish this video. Take a step back and just ask yourself, yes, I know I had to use the law of sines here, but what type of case were we actually given? And if I highlight what we were given, we knew this side, we knew this side, so that's two sides so far, and we knew was this angle over here. What type of case is that? Well, that's an SSA. And ask yourself, well, if this was an SSA, shouldn't I have checked for two possible triangles here? How do I know for certain that there's only one possible oblique triangle? And think about that for a second. And the answer is the fact that we were given this statement here, that Washington, D.C. is directly due east of Gotham City. There is no way that the path from Metropolis to D.C. could have been any other place while maintaining D.C. being exactly due east of Gotham City. If we were to kind of take that side length and just hinge it around and maybe say, oh, what if D.C. were down here? Then it still wouldn't be due east of Gotham City. So there's exactly only one triangle that could have existed here. We wouldn't need to show that, but I did want to make sure that you at least thought about that here.